Okay, so your first job in this is to basically fast forward until we come to a point where things look new. Depending on how far we got in class today, you may or may not have seen the beginning part of this, so feel free at any time to fast forward and get yourself to the point where you have not yet been. So we did the Oreo thing in class today, and really that was just to introduce you to this idea of percent composition, the idea that when you have a whole something, you can figure out how much kind of all the different pieces bring to the whole in terms of mass. So let's take a look at kind of the chemical application of that. It says you can determine the percent composition of a compound by calculating the mass percent of each element in it. The best way to see this done is to work through an example. So here we go. This is carvone, C10H14O, the substance responsible for the smell of spearmint oil. What is the percent mass of each element in carvone? So I want you to kind of have in the back of your mind the Oreo example that we did in class, and really think, if you think about what's the very first thing that you did with that Oreo, you put it on a scale and you found its mass. So what would the equivalent be of finding the mass of carvone? And the answer is the first step is to calculate the molar mass. So you're going to look on your periodic table, and we're going to see that carbon, we have 10 carbons, and we have a mass of 12.01 for those. And notice I'm writing these all down because I'm going to use these numbers again later. So I'm saving myself a step. 14 hydrogens at 1.008, and then 1 oxygen at 16.00. So I'm showing all my work here. So that's going to be 120.1, and then 14 times 1.008 gives me 14.112. Oh, actually, I'm not going to put the 2 on the end because I need my significant figures. And then the last one's 16.00. Add up all those numbers. I'm going to get 150.2 grams with sig figs. So that tells me basically how much that whole thing weighs altogether. That's not the full question, though. The question is asking the percent mass of each element. And so what you're going to do is pretty similar to what you did with the Oreo. Just like you found out the percent mass of the cream filling, the percent mass of the cookie, we're going to do that with all of the elements involved. So let's do a little color coordinating here. We have carbon, we have hydrogen, and then we have oxygen, or the 3 elements involved. So for carbon, we know that 120.1 is the mass brought by carbon to this molecule. So it's most of the mass. We're going to take that and divide it by the molar mass, how much it weighs altogether. Hydrogen, we're going to do the same thing. We know hydrogen accounts for 14.11 grams. Divide that by the whole. And then for oxygen, same thing, 16.00 grams divided by the mass of the whole. I forgot, the unit should be grams in all of these. So let's just sneak those back in. So take out your calculators, and if you have not done so, make sure you have your periodic tables handy because you will use those a lot in this one. So we're looking at, in each case we're going to get a decimal, and then I'm going to multiply that number by 100 to convert it into a percent. And in each case I can keep 4 sig figs, because remember, when we're multiplying and dividing, we keep the same number as the number that has the fewest. And so each number in all of these problems has 4. So that means for carbon, when I get that answer and multiply that answer by 100, I'm going to get 79.96%. I'm going to do the same thing for hydrogen. 14.11 divided by 150.2 times 100. And then for that answer, I'm going to get 9.394%. And then for the last one, 16 divided by 150.2, that's going to give me 10.65%. And I multiplied by 100 there too. Now remember that because of sig figs, our numbers might not add up to an even 100, and that's okay. But what we've just done is we found out how much by mass each of these elements bring to carbone. Carbon comes up with most of the mass, and then the rest is distributed between the hydrogen and the oxygen. So put this idea kind of in your brain, shuffle it to the side for now. We're going to move on to what is going to seem like a very different idea, but they're actually very connected. I'm going to show you here in a moment. The next idea is something called empirical formulas. What is an empirical formula? Nothing to do with the Holy Roman Empire or the Empire in Star Wars. It is the lowest whole number ratio of elements in a formula. So what does that mean, the lowest whole number ratio? Well, I've given you two examples down here at the bottom, glucose and ribose. And you can see I've supplied the formula. If you'll notice, both of these formulas can be reduced. And so what I'm looking at with glucose is I see a 6, a 12, and a 6. Well, those can all be reduced by a common factor to CH2O. And if I look down at ribose, the same thing happens. 5, 10, and 5 goes down to 1 carbon, 2 hydrogens, and 1 oxygen. So we would say that glucose and ribose have the same empirical formula, meaning they have the same ratio of elements in their formulas. But we need another term, though, because in real life, glucose and ribose are not the same element. And that brings us down to the second bullet point here. How does an empirical formula differ from a molecular formula? Well, the empirical formula is what we said right up there. The molecular formula is the actual chemical formula. So in this case, the C6H12O6, this is the molecular formula. It's what it actually is in real life. No reducing down to the ratios or anything like that. It's what it actually is in real life. Okay, cruise over now to the next page. Now let's bring those ideas together. We can calculate an empirical formula. There's actually a way to go from the percent composition of an element into its empirical formula, and that's what I'm going to show you here. There's a cutesy little formula, a poem that will help you remember how to do this. Percent to mass, mass to mole, divide by smallest, multiply till whole. So let's take a look at what that would look like in this problem. Here's your example. Methyl acetate is a solvent commonly used in paints, inks, and adhesives. When methyl acetate was chemically analyzed, it was discovered to have 48.64% carbon, 8.16% hydrogen, 43.20% oxygen. Based on this data, find the empirical formula for methyl acetate. So what I'm going to do is walk you through all 4 steps of this poem. Let's zoom out here with this as an example. The one thing I'm going to do is assume that I have 100 grams of the compound. The reason that I do that is because it makes it really easy to go from percentages into a mass amount. All I have to do is just assume that I have 100 grams. I could start with however much I want. 100 grams, though, makes the math really, really easy. I'm going to kind of divide my paper into 3 rows, 1 for each element in the compound. Let's look at all these steps here. Step number 1, percent to mass. This is the easiest one. This is why I assume I have 100 grams. All I do is I'm going to look at the percentages. I'm going to cross those out and write grams instead. So that means for carbon, I'm going to say I have 48.64 grams of carbon, 8.16 grams of hydrogen, 43.20 grams of oxygen. So step 1, done, check. Step 2, mass to mole. Okay, these are T-charts, and we remember how to do these. So we set up. Remember, the whole goal of the T-chart is to cancel out the units that we don't want and convert to the units that we do want. If grams are up here in the upper left, I know grams are going to go down there. I'm going into moles. So that's going to be 1 mole there. And then where do I find the number that goes on the bottom right? I look on the periodic table. That's the molar mass. So for carbon, that'll be 12.01. For hydrogen, 1.008. And then for oxygen, 16.00. By the time you're done with this, you're going to get really good at memorizing molar masses on the periodic table. It's going to be great. So and solve for those three amounts. 48.64 divided by 12.01. I can keep 4 sig figs, so 4.050. You'll see that 499 there. We'll round up to 50. And then we have 8.10. Again, we have some weird sig fig roundings on these. Don't sweat it too much, though. They won't all be like this. And 2.7. Moles, moles, moles. I'm going to add, ooh, I forgot, I'm going to add 2 zeros onto this because I need 4 significant figures. Okay, let's take a look at what's next. After that, we go to, so we can say mass to mole, check. Divide by the smallest. What does that mean? So remember that ultimately we're trying to come up with a ratio here. And what this is telling us is that for every about 4 moles of carbon, I have about 8 moles of hydrogen and about 2.7 moles of oxygen. It's not particularly helpful. I want to reduce it down by dividing everything by a common factor. In this case, divide by the smallest means look at these 3 numbers that I have. Pick whichever one's smallest, in this case 2.700. I'm going to divide each of those numbers by 2.700. And what that will do is that will kind of reduce everything to a more common factor. It's going to be easier to compare and ultimately find out how many pieces, like how many carbon atoms I have. So I know this is going to be 1. 4.050 is going to give us 1.5. And you'll start to notice these numbers are going to come out pretty darn clean, meaning it's going to be these nice kind of whole numbers. Okay, so this is an easier ratio to work with. But there's a problem. If I was to write this as a formula, I can't say I have 1.5 atoms of carbon, which brings us to our last step. Multiply till whole. What number would I have to multiply 1.5, 3, and 1 by in order to end up with all whole numbers? I can multiply them all by 2. And notice, whatever I do to one number, I have to do to all the other numbers, even if they're already whole. 3, 6, 2. My empirical formula is C3H6O2. Okay, let's try another one. These will get easier and faster too as you go. All right, a certain compound yielded the following percentages. Nitrogen, I'm going to actually write this as I go to save us some time. 2.16. Carbon, 8.392. Oops, sorry, that's hydrogen. Carbon, 12.50. And oxygen, 49.95. So again, remember my first step, I'm going to click around here, is percent to mass. So all I'm going to do is take those numbers, toss out the percent, and write grams. Doobity-doo. Nicely done. After that, mass to mole. So let's set up some T-charts here. We're going to convert all of these from grams into moles. And I don't know who left you not much space. Who made this handout that made it so squished? Okay, so we have 14.01 grams, 1 mole. And if you feel like, okay, Miss PB, you know what, I totally get this. I got it. Go ahead and like fast forward through this. Cruise on to the next one. And I mean, get the right answer, do the problem, but you do not have to stay stepwise through me. If you think you can go faster on your own, oh my goodness, please go faster. You do not have to stay lockstep with me at any time. Okay, so here we go, 29.16 divided by 14.01, 2.08. So again, I'm writing out, I'm keeping my sig figs, keeping track of all that. There's kind of a lot to keep track of in these problems, but the more you do, the more fun they will get in a quietly nerdy way. 12.5 divided by 12.01, 1.0. Again, in all of these problems, if you'll notice, I'm keeping 4 significant figures. Okay, so let's go back to our steps. So we percent to mass, mass to mole, divide by the smallest. I'm reading that poem up at the top. The smallest is 1.041, so that's what I'm going to do in each case. divided by 1.041 divided by 1.041. Gosh, I did not leave much space for this problem. I apologize. Okay, so now let's crunch some numbers. And once we get to this step, things should start to look a little cleaner. Now, if you'll notice, I got 1.99999. Remember that with sig figs, we can keep 4. That number is going to round up to a nice even 2, which is good. That's what we like to see. You should never end up with something that's really, really close. This one did the same thing, 7.997. That we are ultimately going to round up to an 8. It's so close that we can just round that up to an 8. We know that's going to be a 1. 3.122 is our last one. And again, 2.99999, that's a 3. Let's look at our last step. Multiply till whole is our very last one. Well, if we look, this one, the job is kind of done for us. We are already at all whole numbers, which means we're done. We can write our formula, N2H8CO3. Okay, so once you're at this point, take a little shakeout. We got one more thing that we're adding on to this. So you're doing great. Stay with me. Has to do with the molecular formula. And if you remember, if we scooch back here, the molecular formula is the actual chemical formula. What if you get all this percentage stuff? But I actually want you to find out not just the lowest ratio, but what the actual formula is. So let's take a look. The first one, if you are given mass data or percent composition, you can figure out an empirical formula. If you're also given the molar mass for the compound, meaning like the actual compound, you can go one step farther to its molecular formula. So let's take a look here. Here's our sample problem. Succinic acid is a substance produced by lichens and fungi. Doobity-boobity-boo. Ultimately, what I want to know is that percent information. Carbon, we're clocking in at 40.68. And if you'll notice, I'm going to do the first step already. I'm just going to write it in grams. I'm going to save myself some time. Hydrogen, 5.08 grams. And then oxygen, 54.24 grams. So I'm saving myself a step and just doing the percent to mass. The next part, percent to mass, mass to mole. Remember how I said that you're going to probably have these molar masses memorized by the time we're done. And again, at any time, if you're like, yeah, Ms. PB, I know how to do this, let me just go. Stop, fast forward. You do not have to stay lockstep with me at any time, because these are going to have a very repetitive nature to them, which can be both good and bad. Okay, so 40.68 divided by 12.01. But hopefully, if you notice, we're starting to get faster with these problems. So that's always good. 5.08 divided by 1.008. Again, this one, remember, I can keep 3 sig figs. 5.04. And then last one, 54.24 divided by 16. 3.39. So percent to mass, mass to mole, divide by smallest. It's close. Carbon and oxygen are almost the same, but carbon is just a little bit smaller. So I know this is going to be 1. 5.04 divided by 3.387 gives me, see, I get 1.48888. That's really 1.5. This is the only time you'll ever hear me say that you kind of stop thinking about sig figs at this point, but you really kind of do. That's the only time you'll ever hear me say that. Okay, last step, multiply till whole. Remember that I have to multiply all of these by the same number. So the smallest number that will get me to whole numbers is 2, which means I'm going to be C2H3O2. That is my empirical formula, but let's keep going. Remember, we're not done yet. You guys are doing great. I know this is a little like, woo, stay with me. Once you've obtained the empirical formula, you can figure out its molecular formula. So here we go. It says calculate the empirical formula mass. This is basically another way of saying it's the molar mass of the empirical formula. So that thing that you just figured out over on the previous page, the C2H3O2, we want to know what would the molar mass of that be. So let's figure that out. We have 2 carbons, 3 hydrogens, and 2 oxygens. So here we go. 24.02, 3.024. Oh, I do not need a calculator for that one. I think I can do that one. Okay, next thing, you add them all up. So we have 32 plus 3.024 plus 24.02. So with sig figs, I can keep 2 after the decimal, and I am left with 59.04. Okay, so that is the mass of my empirical formula. Let's look at the next step. Divide the molar mass of succinic acid. I was given this in the problem. Let's go find it. Let's read the problem here. Here it is. Succinic acid has a molar mass of 118.1. So how will that be handy? Well, I take the molar mass of succinic acid. This is the real one, the 118 point, I forgot what it was, 0.1, and divide it by that empirical formula mass, that thing we figured out right up there, 59.04. I want you to notice something important. Whenever you do this dividing step, the number on the top should never be smaller than the number on the bottom. It should either be bigger or the same size, but it should never be smaller. If it's smaller, you probably put the wrong one on the top or something has gone terribly wrong. When I divide those two, I get a number that's really close to 2. I'm just going to call it 2. And this is the final part. Multiply each of the subscripts by the number you calculated above. So I know C2H3O2. I'm going to multiply each of those numbers by 2. Take each of those times 2 to get my molecular formula, C4H6O4. So see how that's kind of all connected together. All right, you guys are still with me? You're doing great. We have one more to try, and then we'll be done, I promise. Okay, this is going to do the whole thing. So we're going to go first find our empirical formula. I scan the problem, and I write it as I go to save myself some time. Notice how I always label it with what element I'm talking about. Again, I'm doing my first step right away, just converting straight into grams. Save myself one step. So here we go. We are in grams. Percent to mass. The next step, mass to mole. Grams is 1 mole. 12.01. Like I said, you're going to get some of these molar masses you will be saying on your deathbed. You'll always remember carbon, 12.01. And again, nitrogen, hang on. I'm looking at a different, I might have a slightly different periodic table than you do. Mine says 14.01 grams. If yours says 14.00, just go ahead and roll with it. I don't think our answer should be dramatically different. So I'm left with, again, remember, I'm not doing any rounding yet. I'm keeping all my sig figs. One kind of mistake that some people make when doing these problems is they start rounding and forgetting about their significant figures too early. Don't do that. That only happens at the very end. Oh, this is interesting. Okay, so look at this. In each case, I got the exact same number. So for the divide by smallest step, that's pretty darn straightforward. I'm dividing in each case by the same number. And notice too, there's units, but they all get canceled out. I'm doing moles over moles. So everything gets canceled. I'm left with 1, 1, and 1, which means that multiply till whole step is already done for me. My empirical formula is NaCN. But I'm not done yet. The question is also asking for the molecular formula. So let's bop back here for a second and remind ourselves what we do. First, we find out the molar mass of the empirical formula. So of that. So I have 1 sodium. I have 1 carbon. So again, I'm just doing a molar mass calculation. And for that one, I get I get 49 grams. And so here's what that means. Actually, I think technically it should be, nope, that's right, 49. Okay, so I get 49 grams. Let's go back and remind myself what to do next. I divide the molar mass of my actual compound. This always will be given to you in the problem anytime you have to do this. I'm told molar mass is about 50. divide that by that number. These are awfully close. So if I do 50 divided by 49, I'm left with something that's almost 1. This is the part, remember, where I said you kind of can ignore sig figs. It's always going to be a whole number. I get 1. So that means I multiply each thing in the empirical formula by 1, which is just going to leave me with the same thing. So this is also my molecular formula, NaCN. All right, nicely done. I hope you stayed with me. Thank you, and bring this completed to class next time. And that is where we will pick up in class again.